We're going to shift to section 7.2 today, dealing with properties of exponential functions. Last week we graphed some basic exponential graphs. Can you visualize what an exponential growth curve looks like? Starts kind of flat and then curves up? Yes? Exponential decay does the reverse, right? Starts high and then curves down and flattens out. So we're going to look at those same properties. We're going to look at translations of those. We're going to look at what happens when we have a base of E. We'll talk about what E is. And then we'll start looking at some compound interest questions today, and we'll finish that up tomorrow. Remember, this is a short unit, so we are testing again on Thursday. All right, so parent function, y equals b to the x. Okay, that's our basic exponential function. We can do things, the same transformations that we've been doing to all of our functions. We can put an a value in front, which does what? Stretches, compresses, flips, reflects. All right, so reflection when it's negative, compression when it's something between 0 and 1, stretching when it's bigger than 1. Okay, then we can shift them, left, right, up, down. What is this h value going to do? The things that are with x, move it which way? Left or right. Okay, the thing on the outside moves it up or down. So this is kind of our basic exponential graph that's been transformed. Okay, so we're going to look at what those graphs look like. Starting out, we are going to graph the parent function, y equals 2 to the x. Then we're going to graph y equals 3 times 2 to the x. What should we expect to see? What kind of transformation are we doing? We're stretching. All right, so we have a vertical stretch by a factor of 3. So which coordinates get stretched? Our y's, right? Our y's are going to become 3 times bigger than they were. All right, so for the first one, we're going to use x values from -2 to +2. What do we get if we take 2 to the -2? So the negative's going to flip it, right? The 2 is going to become a 1/2, and then we're going to square it. So 1/4. 2 to the -1, 1/2. Good. 2 to the 0. Good. 2 to the first, and 2 squared. Okay, let's go ahead and plot those. So -2, we're at 1/4. -1, we're at about 1/2. 0, 1, 1, 2, and 2, 4. Looks like a basic exponential curve, right? Exponential growth. If we go to do this, my x's do not change, but you said my y values, what happens to them? They get multiplied by 3. So instead of a 1/4, we're going to be at 3/4. Instead of a 1/2, we're going to be at 3/2. Instead of a 1, we're going to be at 3. 2 now becomes 6. 4 becomes 12. All right, our y coordinates are just getting multiplied by 3. So plotting those. Will it still level off just above the x-axis? Yes. So we have a steeper curve, but it's still going to level off right above the x-axis. What would the domain and range for this one be? X is all reals, good. Y? Greater than 0, good. All right, so y being greater than 0, that's because the horizontal asymptote is where? The x-axis, which has what equation? Y equals 0. All right, so we do have that horizontal asymptote at y equals 0. Okay? And all my y values have to be above that. Questions on that one? All right, talk at your tables about the next one. What kind of transformations are we going to see? All right, I heard reflect over the x-axis. Do we agree with that? And that's because of the negative? What else happens? Good, vertical compression. By a factor of 1/3. So now instead of my y values getting multiplied by 3, we're actually going to divide them by 3, right? Times by 1/3. Okay, let's start with our parent function. Y equals 3 to the x power. Let's go ahead and use those same x values. All right, so -2, -1, 0, 1, 2. 3 to the -2. Good. What's 3 squared? Remember that relationship, right? 3 to the second power is 9. 3 to the -2 is the reciprocal, 1/9. So 3 to the first is 3. 3 to the -1 would be 1/3. And anything to the 0 is 1. All right? Let's go ahead and plot those. All right, now, when we compress this and reflect it, we could calculate the points using a table, or we could just take our dots and move them. All right, we've done it both ways. I'm going to start with this top one here. We're at a 9, right? So when I reflect it, it turns into -9, but then I have to multiply that by 1/3. What's 1/3 of -9? -3. So I'm going to end up right here. Yes? So instead of a 9, I'm going to end up with -3. Okay. If I multiply this 3 by -1/3, it turns into -1. And if I take this point, reflect it, I'm here. Multiply by 1/3, I'm up here. Okay? 1/3 of 3 is 1. Okay. My next point was 0, 1. If I reflect it, I'm here at -1, but now I have to make it 1/3 that high. So I'm going to be at -1/3. Yes? All right, I've got 1/3 for my next y coordinate. I'm going to reflect it. Now it's -1/3, and I'm going to multiply it by 1/3. So I'm at -1/9. What's my last one going to be? 1/9 times -1/3 is -1/27. All right. So it's still leveling off, but this time it's leveling off right underneath the x-axis. Okay? All right. Domain. Range. Y is less than 0 on this one, right? Or underneath. Asymptote. I'm going to refer to that as horizontal asymptote, HA. What's the equation for that? Okay. All right. The next statement says a horizontal shift y equals a times b to the x minus h power is the same as a vertical compression or stretch. Now here's why that happens. If I start out with y equals a times b to the x minus h, that is equivalent to a times b to the x times b to the negative h. Think about that for a minute. When we have the same base raised to powers, what do we do with those powers? We add them together. If I add an x and a negative h, I get x minus h. Okay? Then I can rearrange these and put the b to the negative h in front. I'm still multiplying all those pieces together, but now if I group this, that becomes my new a value. All right? Because b to the negative h can be calculated. Those are all going to be numbers that we can figure out. So a times b to the negative h power is just going to be a number in front of that b to the x. So it's very common when you look at a picture and say, oh, I think that moved left or right, and somebody else says, no, I think it's a vertical stretch or compression. You're both right. Okay, now, we're not going to convert them. If it says to move it left or right, we can just move it left or right. We don't have to change that into a vertical stretch or compression. But I wanted you to be able to see that when you look at it, it might look like the other option is happening. Okay? All right, the other piece here in yellow, a vertical shift. So now if we have that k value at the end and we're moving things up and down, it's also going to move that horizontal asymptote. So our asymptote's going to move to whatever that k value is. All right? Let's try moving a few here. The parent function would be what? Just 2 to the x? And we had a table for that a little bit ago. Right? 2 squared is 4, 2 to the first, 2 to the 0, and our negatives. Okay? So let's plot those. And what are we doing to this graph? Everybody, which way are we going? Right 4. Okay? So I can just shift these points all 4 to the right. Am I still leveling off at 0? At y equals 0? Okay. So again, we shifted this all to the right, but you could also visualize it as a compression, right? This point shrinking down, this point shrinking down, getting closer and closer. Okay? Does that make sense? Yeah. Yes? All right. What transformations are happening on this one? Okay, we have a vertical stretch by a factor of 20, and then what? Okay, so we're going to have some big numbers on this. We're going to have to adjust our scale a little bit. Let's start out graphing our parent function, y equals 1/2 to the x power. What shape will this be? It's decay, right? It's going to start high and come down. Okay, let's make a table. What happens when we take 1/2 to a -2 power? The 1/2 flips and becomes a 2, and then it gets squared, so it becomes a 4. Okay, 1/2 to the -1 power. 1/2 flips and becomes 2. Anything to the 0 is 1. 1/2 to the first is 1/2. 1/2 squared 1/4. Now, we said we have to do a vertical stretch by a factor of 20. That means all of my y values are going to get multiplied by 20. Okay? So let's look at what that would be. So the 4 is going to turn into, when I multiply by 20, it's going to turn into 80. The 2 becomes 40. The 1 becomes 20. The 1/2, half of 20 is 10. 1/4 of 20 is 5. Yes? And then what's the last thing I have to do to these? I have to move them all up 10. So I'm going to be adding another 10 to all those values. Yes? So we probably don't want to go by 1s on our scale. Let's go by 5s. All right. We're going to go ahead and graph this one. All right, that T-chart with the 20 already in there, since our numbers are so big, and then we'll shift everything up 10. So the 80 is going to be off my graph still, going by 5s, but I can get this one. -1 is at 40, 0 I'm at 20, 1 I'm at 10, and 2 I'm at 5. So it still looks like our decay that we said it should. This one would level off where? If I just connected the dots I've already graphed. It's leveling off at 0, yes? But we said we have to shift everything up 10. So when we go to move our points and move up 10, we're going to be here, here, going by 5s. We're just 2 spaces up from where we were. But now I'm not leveling off at 0 anymore. I'm leveling off at 10. So this horizontal asymptote is going to be here at 10. And my graph should be coming down and leveling off right above that. So which transformation affects the horizontal asymptote? The K value, right? That vertical shift. All right. Domain, range, and asymptote for this one. Domain are all reals. Range. This time y is greater than 10, and the horizontal asymptote has what equation? Y equals 10. Okay? All right. Our next one is an application. It says the best temperature to brew coffee is between 195 degrees and 205 degrees. In your packet, the degree symbol did not come out right. It looks like little asterisks. Please change those to degree signs. Coffee is cool enough to drink at 185 degrees Fahrenheit. The table shows temperature readings from a sample cup of coffee. How long does it take for a cup of coffee to be cool enough to drink? If we just looked at the table, we would say about how many seconds? Or how many minutes, sorry. It happens somewhere between 0 and 5, right? Within the first 5 minutes, it's cool enough to drink. Okay. They want it more precise than that. So we are going to create a stat plot in our calculator, and we're going to let the calculator come up with an equation for it. So grab your calculators. We're going to start out entering our data. That we do by hitting the Stat key and choosing Edit. All right, so I want you to enter the data from your table in lists 1 and 2. I'll pause the recording and give you a minute to do that. All right, we have a couple of settings to look at. Based on our data, our highest list 2 value is 203. all right? And our highest list 1 value is 30. So I'm going to go to my window, and I'm going to go from -5 to 35, so I have a little cushion on the edges. Okay, and I'm going to go from 0 to 250 for my y values. Again, I just want a little cushion. Okay. Also notice that my x scale and y scale I put at 0. That just means it's not going to put tick marks in there. All right, so -5 to 35 for x and 0 to 250 for y. The next thing we have to do is tell our calculator to do a stat plot, to graph these statistics. All right, so to do that we do second y equals. We're going to choose the first one. We're going to make sure it's on. We're going to make sure it is a scatter plot, the first picture. And we're going to have it use list 1 and list 2 for now. Okay. All right, if I look at the graph now, hang on, I'm going to take out my equations here. All right, you should see that. Yes? Does it look like it's exponential decay, like there's a curve to it? Yes. All right. So it makes sense that we have an exponential model for this. So exponential model seems realistic based on our picture. Now, when your calculator figures out an exponential equation for this, it is assuming that we have an asymptote at 0. Okay? But in this context, I want you to think about these temperatures. The temperatures are cooling down, right? Are they ever going to cool down to 0 degrees? No, because room temperature isn't 0 degrees. That coffee is going to cool down until it hits room temperature, and then it's going to stay there. So they're giving us an average for room temperature of about 68 degrees. So what we're going to have to do, our data here is assuming an asymptote at 68. We're going to level off right about 68 degrees. The calculator wants us to move that down to 0. Okay? So what we are going to do is we're going to tell our calculator, take all of these list 2 values and just subtract 68 from them. Okay? We're going to move everything down 68 so we can figure out the curve, the equation for the curve, then we'll move it back up to finish it up. Okay? But for the calculator to do this, it's assuming it's supposed to level off at 0. Okay? So to do that, a quick way is to tell our calculator, make another list and take all of your list 2 values and subtract 68. We're not going to do them by hand. We're going to let the calculator do them. So let's go back to our stat, edit. I want you to go over to list 3 and arrow up so you're in the place where it says L3 in that little cell. Okay? We're going to put a formula in that. So I'm going to tell it, take second 2, take list 2, and subtract 68. Okay, so right down here, you're going to see a formula that was typed in. And when you hit enter, it's going to create that list for you. Okay? Does that make sense? So you don't have to subtract by hand. Your calculator can take them all and subtract 68. Okay, so what we are going to do now is tell the calculator, use list 1 and list 2, sorry, list 1 and list 3, and come up with an equation. Okay? To do that, we're going back to stat. We're going to calculate, and you have to scroll down to 0 where it says exponential regression. That's the one we want. We want it to come up with an exponential curve. Okay? So exponential regression. We're going to tell the calculator use list 1 and list 3, our adjusted values. I'm going to go ahead and store it so that I can show you on the board here the picture. If you don't want to store it, that's okay. To store it, we're going to do variables, y variables, function, y1. Okay? If you have the older version of your calculator, when you put in exponential regression, it's waiting for you to do list 1, comma, list 3. Okay? Hitting enter. It's coming up with an equation for me. Now, notice at the top, y equals a times b to the x power. Yes? What did they give me for a? 134.5, roughly. And what did they give me for b? 0.956. So can we write our equation? So we have y equals 134.5 times 956 to the x power. Okay? Now, our data, we moved down 68 degrees, right, to come up with this curve. We now have to move it back up 68. Okay? So, we are going to use this version. We found the right curve, and I can show you on the calculator here. Our dots were up high, right? And then we said we have to move everything down 68. So the equation they're coming up with is 68 down. Yes? But we have to move that curve back up 68 to hit those dots. Okay? All right, now it says, how long does it take for that cup of coffee to cool to 185 degrees? Okay, we have our equation. So you're going to enter in your calculator, y1 equals 134.5 times 0.956 to the x power plus 68. And put a second one in, just 185. That'll be a horizontal line that comes across, and we can figure out where these intersect. Okay, so put those in your y equals. Okay. All right, so when we graph it, now you can see that we moved that curve back up to the 68 degrees higher that it should have been. We're looking at the red line coming across at 185. How do we find that exact point where they intersect? Second trace, yep. Second trace, we want to do option 5, intersect, and enter, enter, enter. So we're ending up with it reaching 185 degrees at about 3.1 minutes. Okay. Questions on that one? Yes. All right, so up until this point, we have worked with rational bases. So our bases were things like 2 or 1/2. All right? Exponential functions can have irrational bases. There's a very famous one. We use the letter E to represent the number. It's kind of like pi. When you see the pi symbol, you think 3.14. When you see E, you're going to think 2.718. Okay? The number comes from this. If we were to graph this or look at a table of values, as our x value gets bigger and bigger, so as we head towards infinity, you can see that the y values are getting closer and closer to that 2.718. And if we kept going, so 10,000, 100,000, right? If we kept going, this y value is going to get closer and closer to this. Okay? Now, when you see an E in the formula, if you're trying to visualize what that graph's going to look like, think of it as a 3. 2.718 is very close to a 3, right? So your graph's going to look really close to there being a 3 in there instead of a 2.718. Okay? We call that the natural base, so we refer to these as natural base exponential functions. But all of the properties that we've been using still apply. So if I gave you this, x minus 5 plus 7, 2e to the x minus 5 plus 7. Describe the transformations. What is the 2 going to do? Vertical stretch. What's the 5 going to do? Right 5. The 7. Up 7. Right? It's going to do the same moves that your normal exponential graphs would, because it's going to be very similar to this. Right? Instead of an E, we think of it being about a 3. So if you had to picture your graph, you could use the 3 version. Okay? On your calculator, there is an E button and there's an e to the x button. If you're asked to evaluate, say, e to the third, you have a few options. You could graph y equals e to the x and then look at a table, figure out what when x is 3, what your y value is, or you can use that e to the x key. On your calculator, it is right here. Okay? So use your calculator. We're going to find e to the third. All right, so e to the third, we should have 20.086. All right, go ahead and find e to the 8th. E to the 8th, you should have 2,980.958. Are we getting those? Okay. Shifting gears a little bit. Have you heard of compound interest? All right, compound interest is where your interest gains interest. All right, so you put some money in the bank, and after a certain amount of time, the bank says, here, I'm going to give you some interest for letting me use your money. Okay, now the amount you have in the bank is bigger. Now when the bank says the next time, here's some interest, thanks for letting me use your money, you're going to get more interest because what it's basing it on keeps getting bigger. So your interest now earns more interest. Okay? It's called compound interest. There are different scenarios. Things can be compounded annually, semi-annually, quarterly, daily, monthly. There's different options. The one we're going to look at today is where it's compounded continuously. Tomorrow we'll look at all those other options. It's a slightly different formula. So I want you to think back when we first started talking about exponential growth or decay. We had the equation a equals p times 1 plus r to the t power. Remember that? Okay, this is when it's not compounded. Okay, so if it doesn't say anything about it being compounded a certain number of times, you're going to base it on that one. If it says it's compounded continuously, there's a different formula you need to use. We call it the PERT formula. A is still your final amount. T is still time. R is still your interest rate converted to a decimal. P is still your starting amount. But instead of the 1 plus R to a power, you have e to the RT power. Okay? All right, so the first one says, suppose you won a contest at the start of 5th grade that deposited $3,000 in an account that's paying 5% annual interest, compounded continuously. I want you to underline that, highlight it, put a big star next to it. As soon as you see that, those two words, compound continuous, you have to know it's PERT. Okay? So A equals P times E to the RT power. Our final amount is what we're trying to figure out. What is the principal or starting amount? 3,000. We have E already built into the formula, and our power now is our rate times time. What is the rate they gave us? Okay, so 0.05, and I'm going to put a T in there because that's the model. Remember we talked last week about needing a model first. Now use that model to figure out how much we're going to have after 4 years. Okay, so A would equal 3,000 e to the 0.05 times 4. Go ahead and grab your calculators. 3,000 times e to the 0.05 times 4 power. And we're going to just round our answer to the nearest dollar. All right. Are you getting 3,664? Okay. What if we leave it in there so that we got the money when we started 5th grade? We're checking how much we have when we start 9th grade. What if we leave it in there for 4 more years? Now what is our time value? All right, so we need 3,000 e to the 0.05 times 8. Remember, you can just do second enter and it'll recall your last calculation, and you can just change that 4 into an 8. And you should end up, rounding to the nearest dollar, $4,475. Okay? So you haven't done anything. You put $3,000 in the bank, and 8 years later, you have an extra $1,475. Okay? All right. Before you start your homework, I do want to go over one other formula. Have you heard the term half-life? It's typically used when we talk about like radioactive substances. Okay? The half-life is a time that it takes for half of that material to decay and no longer be radioactive. Okay? If you're setting up your formula, you are still going to start with your initial amount. Your decay factor is going to be 1/2, right? We lose half, we keep half. So that would be 1 minus 0.5, which is still 0.5. The difference here is the power. So I'm going to give you an example. We're going to start with 50 grams of a substance. Okay? Its half-life is 20 years. How much are you going to have? We would have to set this up, and our power would be whatever the total time is divided by 20. So let's say we want to figure out how much we have after 100 years. We're not cutting it in half 100 times. Over that 100-year span, it's only getting cut in half 5 times, right? Every 20 years, it's gone down half of what it was. So I would have to put 100 divided by 20 as my power. Does that make sense? Okay. Assignment is written above here. There should be graph paper on your table.